In this video, we'll introduce defective matrices. This is what we call it when an n by n matrix doesn't have n linearly independent eigenvectors. We'll look at the case where A is a 2 by 2 matrix for now. The higher dimensional case has its own section devoted to it. Before we do anything with systems, let's remind ourselves of the previous work we've done when we had a single linear differential equation. For example, y double prime plus 4y prime plus 4y equals 0. We set up the associated equation x squared plus 4x plus 4 equals 0, and we solved it. In this case, x plus 2 squared equals 0 to get a solution x equals -2, which gave us a solution to the differential equation e to the -2t. We then asked ourselves if we could find a second solution of the form u of t e to the -2t. And we found that for this to work, u double prime equals 0, i.e. u must be linear. So we created a general solution, y equals c sub 1 e to the -2t plus c sub 2 c sub 3 plus c sub 4t e to the -2t, which we then simplified as a e to the -2t plus b t e to the -2t. Now, back to our current setting. X prime equals ax. With this in the back of our mind, suppose we have worked with a 2 by 2 matrix and gotten a characteristic polynomial with a single root, 1 eigenvalue to lambda. If this eigenvalue has two linearly independent eigenvectors associated with it, this doesn't matter, but suppose it doesn't. We can only find one linearly independent eigenvector V. Well, this allows us to create one solution, V e to the lambda t. The obvious, based on previous experience, would be the following. V t e to the lambda t for our second solution. But is this a solution? Well, let's plug it in here and here. We take the derivative as usual using the product rule. The fact that this constant is a vector doesn't change the calculus. V times e to the lambda t plus lambda t v. Sorry, we pulled the v out. Plus lambda t e to the lambda t equals a v t e to the lambda t. Because these are non-zero, we can divide both sides by e to the lambda t. V times 1 plus lambda t equals a times v times t. Rearranging v plus v lambda t equals a v t v equals AV minus lambda V times T. And this is a problem, because this solution is supposed to be satisfied on some interval. T is a variable. It needs to be able to vary. But this is a constant, and this is a constant. There's either one value of t that satisfies this, or no values, depending on whether this is a constant multiple of this. But it's certainly not true on an interval. However, if we think back to the earlier material, getting solutions of the form t e to the lambda t only occurred after simplification. And maybe that simplification simply doesn't work when we have vectors. Originally, before we combined like terms, we had a linear term. Let's try that. A proposed solution V T plus W E to the lambda T. We'll plug this into X prime equals AX and see what falls out. After we simplify and divide out the non-zero e to the lambda t terms, this will give us v plus lambda w plus lambda v times t equals AW plus AV times t. And this can be true for all real numbers t, not just one or two of them. All we need is for lambda v to equal AV. So these terms are always the same. And for v plus lambda w to equal AW. So these terms are the same. This condition says that V is an eigenvector, i.e. A minus lambda I times V equals 0. This condition can be rewritten A minus lambda I times W equals V. This is an eigenvector-like condition, but instead of having 0 here, we have this eigenvector. We call W a generalized eigenvector. So, theorem. Let x prime equal ax, where a is 2 by 2. Suppose we have a single eigenvalue, lambda, and a single linearly independent eigenvector V. Then the general solution is x equals c sub 1 v e to the lambda t plus vt plus w e to the lambda t, where w satisfies the equation a minus lambda I times w equals v. Furthermore, if we're in this situation, such a w always exists. In this video, we have seen how to deal with a repeated eigenvalue that does not have multiple linearly independent eigenvectors associated with it. We have only considered the 2x2 case so far, but this will generalize in a fairly natural way in a future section.